I'm starting the stream. Welcome back. This is Chill Maths on Twitch. I'm James Monroe, and we're going to talk about classifying quadratic forms again. I've been working on the intro. There we go. Right, here's the plan. Last time we were trying to find all quadratic forms with a particular discriminant, looking for ones that were the same up to some symmetries. We had one case left to check for, I believe it was called question 1 in the questions in here somewhere. So I think I'm going to try and do last case 148, which is a positive number. So we're looking for elliptic quadratic forms. As the plan. I think 145 took us about half an hour last time round. We ran the stream long. Hello, Maths2222222. Good to see you. So I'm going to have a quick look back at what we did last time for 145, and I'm going to try and do it for 148. Those numbers are very similar. I'm expecting them to be very different in practice. So we had this, and we drew this horrible red tree over here, which was just one case, to try and split up the cycles of all the possibilities over here. We had some relationship, didn't we, that h squared minus pq was supposed to be equal to h squared plus pq might be equal to something. H squared plus 4pq possibly. Let's look up here. Yeah, h squared plus 4pq was supposed to be last time 145. This time 148. Right, I don't always do this, but I'm going to add a page, I think. Oh my goodness, was that the command for add a page? No. Something mad's happened. I'm going to fix that. How's everyone doing? You all right? Is it just me and Maths22222? Might be. That would be all right. Hope you're well. Whoever's watching. I don't think we've seen this yet. I think I've skipped forward several pages. I'm going to come back a bit. And there's 148. Good. Right. I don't know what I did. Document. No. No, not that. Oh, yes. Add note page. There it is. Good. Right. So 148. Good. Okay. So we want h squared plus 4pq to be equal to 148. And this sets some pretty sensible bounds on how big h squared can be, because I don't want it to be too big. And I think I want h squared to be even, because that's even, and so is that. So I might consider h as 0. That's different, because 145 was odd. So we had these other cases, didn't we? So if h is 0, then pq, let's divide by 4, let's be brave. Hello, if you're just joining, we are doing some of this sort of maths. H squared plus 4 times 37, 120 and 28, 148, good. Which there's only really one solution to that, isn't there? Well, I suppose there's two. We use positive numbers in this. So we might have PQ be 137 or 37.1. Those are, I've remembered, different because of signs of the things. Right, look, I'm trying to remember things as we go along. The next case is h is 2, in which case this side will be 4 fewer. Dividing by 4, we'll get down to 36. And there are really quite a lot of cases here, aren't there? We had some of these last time. 218, and then here we go, 312. How's your week been, everyone? I've been listing factors of 36 for, as far as I can remember now, all of my life. I get bored very easily. But there we are. 4 times 9, 6 times 6 is 36. And then I'm just going to keep going. So then there's the ones that are the other way around. 12, 3, 18, 2, and lastly 36, 1. Slightly ran out of space at the end. Right, well, let's hope that not all of the cases are like that. So if you take off 16, then you're taking off 4 from 37. So you get 33. You have a driving test on Wednesday, question mark? Like theory test or practical? Which stage of driving are you doing at the moment? I have my second driving lesson today. I'm learning to drive. Oh, practical test. Well, good luck. That's the, I don't want to escape, but that's the scary one, right? In the real world. They told me that the pass rate around where I live, the pass rate is about 40%. So that's the whole thing. But just because the pass rate is what it is doesn't necessarily mean anything's going to happen. Right, when h is 6, I'm going to go all the way to 12, I think. Yes, and then stop at 12. So several lines. I hope I get some numbers that are, well, prime would be nice, wouldn't it? 37 was quite a fun case. So 112. 112 divided by 4 is only 28, so I've got quite a few cases there, haven't I? 64. Oh my goodness, look at all these cases. This is incredible. But we're going to do some linear stuff to work out. We're going to do straight lines to work out the cases for the next bit. 128. So it's 4 times 7. Oh no, so tough. I've got to list all the 2's, haven't I? In fact, listing the factors of 28 is something that you end up doing if you're interested in perfect numbers, I suppose. So it might be that reason why I've done a thing. 1, 2, 3, 4, 5, 6. That sounds like about the right number of factors. 3 times 2. And then this last case, if I take off 64, I get 84. Divided by 4 is 21. So coming down by as much as 7, because I've gone up by, do some quick checks, gone up by 28, which means I've come down by 7. The next one I'm going up by 36 in terms of the squares, so this will come down by 9. So I'll go down to 12, I think. Or said differently, 100 over here means 48, divided by 4 you get 12. And then in this last case, I have 144, all the weight going on the h squared. We did what, so Thursday we did a retrospective. I didn't really know if it would work, and I got Rowan on the stream to react to stuff. And I didn't give Rowan enough airtime, I think. An alternative plan might have been to just get Rowan to improvise an episode, which would have been fun, I think. But we looked back for about 2 or 3 minutes, looking back at episodes. Oh, you were there as well. Oh, nice. Yeah, work. 2, 6, or what's this? 3, 4, or 4, 3, or 6, 2, or 12, 1. If you've just joined us, we're doing some maths in a chill way for a question that is set in this textbook that we're reading. We're finding the class number for the discriminants of positive 148. Good. So I've got a case in here which is that h could be 8 for the middle number. We're looking at this quadratic 1 plus h xy. I'm not sure it matters. This quadratic form. Well, there's loads of ways for this to have discriminant 148. I'm listing out all the ways. Hello, famished edits. You're right. Good to see you. We have maths. Right, I think that is a huge list of cases. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32 cases for what an edge might look like in the graph of all of the values of this quadratic form. And some of them will turn out to have the same values because, of course, each individual quadratic form takes lots and lots of values. We can link them together. Into psychology. So the last one had about 36 cases, I think. Let's look over here. Well, not 36 cases because then they split down into only 3 different forms. But if we count these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4, 5, 6, 7, 8, 38 of these. So I suppose count our lucky stars. We've only got 32 of these to deal with now. Let's see if we can work out the maths a bit faster this time. So I'm going to draw a long separator line and I'm going to work towards the right to work out what's going on. So for people who've just joined, we've got this idea that the values taken by a quadratic form, you can put them on a kind of graph with different regions for each of the different xy pairs that you might put in. It's not the standard Cartesian xy way of graphing space, but there are different regions for different pairs of x and y, and rules for what happens when you cross edges between those regions to visit different places. We've got a lovely picture that I'll show you at some point of what's going on there. Right, but the idea is perhaps that P and Q, if you put in 1, 0 and 0, 1, as your starting points, P and minus Q are the values that you see. So I might see 1 and 37, with H being something to do with how the value changes as you move across. So H is 0 here, which means that the sum at the moment is 38. The next thing I see is 0 more than 38, it's 38. which is minus 37, sorry. The sum is minus 36. The next thing I see will also be minus 36. So that's a negative number, I'll put it over here. And h changes as well. So let's think about that. Because this is minus 37, and then going across this edge, the sum, there's this complicated rule that I'm trying to use about how things change. This complicated rule which says that 1 and minus 36 is minus 35, so it's gone up by 2 to get from minus 37 to minus 35. This little geometry topology sort of thing, which is an h value of 2. And it says the next thing that happens is that it changes by 2 again. So instead of minus 37 or minus 35, we see minus 33. And then the story goes, we've got minus 36 and we've got minus 32. That's an increase of 4. So I put 4 as this value here. Okay, I've got these h values along the way, which can go negative, I think, but we're just going to keep going. Okay, and so far, hopefully, if I'm doing this right, all of these are somewhere up here. Let's change colour to blue or something for this blue case. It's blue quadratic forms. These ones are all considered to be equivalent because they have there's an edge there which, if it occurred in the middle, would be a particular simple quadratic form. But we consider ones that have got the same stuff just translated along to be the same quadratic form, equivalent quadratic forms. So far I started up here, 1 and minus 37 are my values, with 0 h value in between, and then I moved to a place over here, 1 and 36. Now I've moved to a case 1 and 33, and you can see I'm going to run out of things. There's only finitely many possibilities, which is a related idea to this idea that this thing is periodic, because there's only finitely many, huge number up here, but finitely many cases that it might be in. Okay, I think the next thing is going to be negative as well, because we're going from minus 36 to minus 32, which is an increase of 4. So the next one up is from minus 32, the sum of this 1 and minus 33. From minus 32, we go up by 4 again to get to minus 28. And I think these are going up by even numbers. I think that's 6 for that gap that we just did from the gap from minus 33 to minus 27. So then we go up again by another 6 to get minus 21. And we're still going through these cases, by the way. It's going to change in a second because we're getting there now. We've got minus 28 and then minus 20. If you've just joined us, I really don't think I can explain this. It's a bit mad. Bear with me 2 seconds. Minus 12. I write 10 over here because minus 21 up to minus 11 is 10. And then this will be a minus 1, at which point we've finally gone through all of these cases along here. We didn't have to explore all of them. There's kind of quadratic form going on. Soon changes, yeah. Hello, Mary, you right? Good to see you. Welcome to Chill Maths again. Time to find out what happens next. Will it just go back down again? Will it just be 1 forever? Doesn't feel right somehow for it to be 1 forever. So we're in this 12 case now. Let's put it above the line. So the sum is now minus 12 goes up to 0, and then after that, the next thing we see, with an increase there of 12, the next thing we see is positive 12. And that's a positive number. Does it go back through the flipped ones? So I'm expecting if I go over to the left, this h of 0 thing, I think means that if I explore to the left, I see these numbers written backwards. I don't quite want to go there. I'm hoping that at some point later we see 1 minus 36 and then 1 minus 37, and we know that it repeats after that. Once you've got an edge and the values above and below, you can use the discriminant to work out h, and then it's fixed, and then you're in the same state that you were in before. So this is like a little journey that we're doing. Okay, so now we're at 111, which is an increase of 10. So this is quite exciting, because then the next thing we're going to see is, instead of 1 or 11, is 21. So now we're increasing the numbers over here. I need to make my lines larger than my numbers. But that was an increase of 8 now from quadratic form stuff. Quadratic form stuff from 12 and 20 is an increase of 8. So it increases by 8 again to 28. This one's got a pleasant pattern to it, hasn't it? Look. We're seeing numbers over here that we saw over there. So I predict that if I keep doing this maths, I'm going to see 36 and 37 next, aren't I? Okay, so after 28, we've got 21, 27, which is an increase of 6. So then, yep, 30. Oh, what have I got? 21, 27 is an increase of 6. Oh, What am I doing wrong? I just said that with a lovely pattern, and then I think I've broken it straight away. 21, 27 is an increase of 6, and then 33 would be 6 more again. Oh, does it go back through these in reverse? Yes, I think it's sort of glide. It's a sort of glide symmetry. But if I tell the truth, I wasn't really paying attention when the book talked about glide symmetry about 2 or 3 months ago. Several pages. If you'd like a copy of the book to find out about glide symmetries, I'm going to keep calculating this. If anybody wants to read something separate, you can get the notes for this book online for free. Maybe you could search the PDF for glide symmetry, because I think that's what we're doing. But I need to carry on calculating, I think. Look at me taking the easy job. So from 28 to 32. No, something's wrong. From 21 to 27. That was a 6, not a 10. And this is a 4, because from 28 to 32 is only 4. Getting there, and then from 28 and 32 is an increase of 4, so then the next one is 36. There, we're good. So I think this is going to be quite well behaved now, isn't it? I would hope. 33, 35, 37, 0. And now we're not in the same place we started with because the numbers are flipped over. But we've gone down here, down this one, down these states, and then we've explored these states. So we're not back where we started, but now I think it's going to turn around and go back again. Okay. Let's just check that, because if this does a state we've already seen, then we know what it's going to do. So from 37 it goes 36 plus to 37, it goes to 36, good. And that's now 37 to... What do I write here then? So 37 to 35, I think I write -2. And that's not really on my board, but I think maybe my board is supposed to say mod h everywhere. Oh, is this something to do with rational roots? I don't know if this is something to do with rational roots. Be surprised if it was rational roots. Why would I be surprised? What am I thinking? Oh, this is nice and periodic. No, does that mean rational roots? I think this means root of a... I think it's mean root of a quadratic is where the continued fraction's going. If you scrolled back in the book to the bit about continued fractions, sorry while I get comfortable, on the creakiest chair I could find, I think it's... I know what you mean. What was the case? If you have a quadratic form like this that goes to rational roots, what does the periodic separated line look like? Oh, no, it is a rational root, isn't it? I think it is a rational root because you're saying that you can do a sort of transformation. And then, no. So no. I still think quadratic, right? I still think quadratic because you could do a rational transformation that represents the glide symmetry, and we're saying that the fixed point of that, as you keep doing that, you get closer and closer to some number. The fixed point is the root of that, but I think the root of that is a root of a quadratic. What does it say about reflective continued fractions? I think those are, we haven't proved it yet, but I think those are the ones that relate to roots of a quadratic. Which is, I think, why we keep finding them here. So then I suppose the question is, what do I think is going on if it's not doing that? If it's not doing that, what do I think it's doing? Because we had some examples where it had reflectional symmetry and some examples where it didn't. Coming out of just the 145 case last week, we looked at some continued fractions. I think I have one on this previous page down here. Or is this going to be a glide symmetric one, isn't it? Here's this red case. What did this do? Oh, so this had this kind of glide symmetry. And then it was periodic. Yeah, I don't think we have this forwards backwards thing going on. Okay, so I don't know what's going on. Yes. Okay, so if you have a zero region, that would be a rational root of your quadratic. Because it'd be a numbers x and y that you could put in for the corresponding quadratic. Ah, Ah, right. Yes, if the real quadratic doesn't have any roots, then this thing doesn't change sign because it's single signed everywhere. Okay. Which I think of as different cases for my quadratic form, but you can also convert it to a quadratic equation and then talk about those. So I think I'm not going to draw in the rest of this, by the way. He says drawing it in. And because it is now boring to me that this goes 1 minus 1, but going this way with a difference of now negative numbers, so that eventually we get down to 1, 1, and then the job is to draw this line from 1 minus 1 with a difference of minus 12. You go 12, 0, minus 12. So then it's going to, and this is going to join up eventually. So we're not quite there, but this is going to go minus 12, 21, 28, 33, 36, and then 37, and join up again and do the same thing again. Good, so that's the blue case. Ooh. Right, so time for the 218 case, which I'm going to colour code red, I think, which is red for you, just about. The red pen's a bit strange, isn't it? The blue pen's a bit strange as well. And the next thing that I can see that's not currently in the case is this 218 thing. Discriminant being positive told us that there is a separator line. Yeah, it's to do with the roots of the quadratic. Yeah, okay. Yeah, it's all connected. So 218 gives us this, and we're starting off in the case where 1h is 2. So that says that currently you have 20, the next, no, minus sign. Currently you have minus 16, the next thing will be 2 larger than that, which is minus 14. So off we go. So red cases, let's put the first couple in just to show what we're doing. We've started with this one to see where we go, and it's gone straight away to 214, which is a difference of, I think h is 6 in this case, let's think, because we've gone from minus 18 to minus 12, that's a change of 6. So the next thing we'll see is minus 6, and this I think will be 10. So in h is 10 to 6 in, oh, it's a bit irritating switching colours, isn't it? 2, 6 over here, back again. Let's see if I can keep doing both without driving myself nuts. We go from minus 14 to minus 4, and then another 10 gives us positive 6. And that's looking across here, that goes from 2 to 0, which is a case of minus 2. Oh, that's quite a weird change. What was I doing? Let's think about it again. I only know the arithmetic progression rule, which is why I'm doing everything exactly one way. Minus 14 to minus 4 is an increase of 10, and then 10 more would give me 6. So I've written this 6, but then reading across 2 to 0, that's a change of minus 2. Do I like that? I think it's this one up here, by the way. So I'll underline that in a second. The Math 2 is ahead of me, and says this one repeats quite quickly. So I'm going to have to do it. I've got to do it anyway. It's good for me. So 2, 0, minus 2. And now I'm looking at minus 6, 4. It's a change of 10. Minus 6, 4 is a change of 10. And 4 again gets me to 14. 10 again gets me to 14. And now I'm looking 6, 12, I think gets me to 18. I'm getting a bit nervous. Am I in even slightly the right ballpark here? Yeah, I'm over here now. This feels like it's jumping all over the place. 6, 12, I guess I could look on the Desmos thing, but is there another way to do this to find the same form? Not that I know of, other than looking at the values it takes and working out which cycles they're in. The book hasn't given us any tips yet for showing that two things are equivalent to work out the class number faster. So here we are, I suppose. Sorry. 6 and then 12, change of 6, which is 18. What's that? Not now. 14 and 16 gets me to 14 and 16 gets me to 18. But I already have an 18. What on earth am I talking about? 14 and 16 gets me to 18. So 18 again. 14 and 16, which is an increase of 2, gets me to 18. 18 and 16 brings me down to 14. Okay, so I think this one goes back again after not that long. Brute force, yes, Hamiltonian dynamics, that's right, we're brute forcing things. Yes, you too can join the brute forcing crew, because I think it's now going to do this. -6, and then there's a 2 here, and then I guess -14, and then -18 again. Then join up. I think I'm going to go through and just label all my arithmetic progressions. 18, 12, 6. 14, I don't like the negative ones. 14, 4 is a drop of -10, and then -14, 14, 4, -6, -2, 0, 2, increase of 2 each time, and then 6, -4, -14 is, I think I'm now just labelling things backwards, aren't I? No, not quite. Oh, yes, quite. So over here 10, over here -10. And then I guess -6. But I should check it just to make sure. -6. Oh gosh, -6, -12, and then -18, which gets us back around again. Okay, to another -18. Right, let's underline the ones in red that we saw along the way. Also, we need to decide whether these do reflection symmetry or not. I think this one does about this line, and I think this one does about this line. So they're each only giving us 1 towards the class number. Okay, so it's underlined some more stuff. So we saw 2, 6, and then we saw 6, 6, which is over here, and then we saw 6, 2, which is over here. Then we saw 14, 2, which is in here, 18, 2, and that's it. That's all we saw. 18, 2, over there. Okay, so it's a second sort of quadratic form with discriminant 148. Will there be a third? Yes, because we've got more things still to go. Oh, everything here is even. This looks like a multiple of, everything's been multiplied by 2. So is it a multiple of the one of the ones we had when the discriminant was 37? So this is not primitive. We've been caught out by that last week. So I'm going to think, oh yeah, so not primitive. Which I don't think was forced on us, but, well, I suppose if H, P and Q have a common factor, then I get suspicious. Any others to watch out for? I can't see any others immediately to watch out for. But these ones where H, P and Q are all even should have been alarming to me. Maybe I didn't need to explore those because I could see, maybe I should have seen that as I'm doing these calculations, I'm always working with even numbers, so all the values will be even, so it won't be a primitive quadratic form. This one is, well, you could say that a canonical example of this is small numbers. A canonical example of this with small numbers is 6x squared plus 2xy minus 6y squared. But then a better example of a quadratic form is just 3x squared plus xy minus 3y squared, which has discriminant 37, I think, which we could have maybe we didn't already find it because we were only dealing with negative numbers last week mostly. Is there a relationship here? Maybe. Certainly we should watch out for all the non-primitive ones are multiples of something with smaller discriminant. So we could, if we'd already done the 37 case, we could, if we'd already done the positive 37 case, we could have found some like 3x squared plus xy minus 3y squared. Yeah, which has discriminant 37. If we found other ones, if we'd found other ones like that, we could be on the lookout for those things multiplied by 2. I think we've found them all now, because cases where everything is even, we've underlined all of them in red. All of the pairs where both numbers are even and h is even are in red now. So we've explored all of them. Maybe I should have, perhaps by reference back to the 37 case, they will fit into, they all go over there. Oh, they have to. So I shouldn't have looked at the things where h, p and q are all even. Right, okay, let's see if I fall for a version of that in a second. one of the hardest bits of this is to not only don't fall for the same trap again, it's that don't fall for the same trap with different numbers or the same idea disguised as a different trap. Right, what am I exploring next? I think it's 312 with h's 2. So we currently have -9. I'm interested in seeing -7 next. And then h will be... So I think I'm supposed to use quadratic formulas for this or something. There's some way of doing this faster than what I'm currently doing. But I don't know what it is. So -12 to -4 is 8. So then the next thing will be +4, which goes up here. 3 minus 3 is a drop of 6. So then I'll see -9. -7 minus 5 is an increase of 2. So then I'll see -3. Oh, down here. I'll see -3 down here. -9, 1 is an increase of 10. So then the next thing I'll see is 11, which goes up here. 4, 8 is an increase of 4. So next, increase of 4. So next I'll see 12. I haven't looped yet, but I have got to something with negatives of where I was before. So now I think it's going to do the same stuff, but with negatives along there until it turns back again. I've got kind of a glide symmetry thing going on. So I'm actually going to stop there and underline stuff. Slightly faster? Is that better? Don't know. Slightly faster. We've explored the edge 312. Then we saw 3-7, which is down here. Then we saw 4-7. Then 4-9. Then 4-3. Then 11-3. Then 12-3. And then it turned around. And I think what I'll see next is 7-3. So all of the opposites of what I've already underlined. So you see from 3-12 I underlined a bunch of stuff, and now I'm at 12-3, and I think it's going to do exactly the opposites from there. It's got this kind of transformation where there's a transformation that moves space or moves space around, but also flips the signs of things. I don't know. Sort of thing that maybe only makes sense in my head. So I'm going to underline all the opposites of the ones I've got. So 4-9, I'm going to underline 9-4 and 3-11. I think we'll see these on the way back. Having seen 4 and -3 together, I think we'll see 3 and -4 together. And I think that one won't have a reflectional symmetry. So I think this has got this contributes to the class number twice. Contributes to class number. And this one contributes, because of the symmetry, 1 to class number. So then I think the answer is 3. If you've been playing along for the last half an hour, I think the answer to this question in the textbook is 3. And now I'm going to try and Google it. How's everyone else been doing? 3 sounds about right. We haven't really found a good list of this, or a good way to do the class number. Because we've got, for example, this list on Wolfram MathWorld, but that only has negative numbers. It has in tiny writing over here. H of -d, scroll, H of -d, which is not what I want, because I would like to know about positive 148 for this exercise. And I think there's something at the back of the book, but I don't think it goes far enough. Let's see if I can find that book. So there's a book. Here's the book we're currently reading, but this version lets me skip to the back, where there is a big table of periodic separator lines of quadratic forms, and also some facts. Here's some facts. Is this 148? Oh yeah, 148. Not negative. Forms of positive non-square discriminant. Oh, brilliant, that's us. And the answer was in the back of the book. Good, they say 3. And they have some canonical examples. 10 -37. Change his notes. 10 -37 is my blue one. That's good. And then they've picked for this one 3 ± 2 -12. That's the two sorts of my grey curve. The plus or minus sign, meaning whether you're going left or right on the H thing. So 3. Brilliant. Okay, I don't know what this character means. I think we're going to learn about that at some point in the next checks notes. 200 pages, because this is on page 140, and this, looking at the back of the book, is page 350. So, in the next 200 pages, I expect to learn what those chi symbols mean. Maybe. Good, well, I'm pleased we got the right answer in the end. Brute force for the win every time. Cool, good. What's that telling me? Right, quick shout out for Imran Part, he followed me 6 days ago while I wasn't live. That's normally when people do that. Right, okay. I think we've now done all of question 1, and I'm giving us a tick for doing question 1. In this extended exercise, we're going to read this one. Hopefully it's not statistics. Nothing wrong with statistics, just seems like that would be a bit of a left turn for this book. I'm going to skim read this extended exercise, but not do it. Because chill maths, we don't do all the exercises. In fact, we normally don't do any of the exercises, but here we are. The only negative even discriminants with class number 1 are these numbers. So all the other ones, maybe you can always find a symmetry, or maybe you can always find 2 different solutions. Even when you find different solutions, negative numbers, Negative numbers was the cases like the ones on the left over here, where we looked at some negative discriminants, and we found these different cases. That's scribbled out, I wonder why. Oh, that's 1 over here for one case. These ones are not primitive because they were multiples of 2. That was a bit annoying. We had these different cases of what A and C might be. Okay, here we are. Let's skim read this. Strategy will be to exhibit an explicit reduced primitive form Q different from that for each one except d equals 7. So we've put the disclaimer even in there. So we're not going to find out that fact about negative 163 today. Probably. In each case, a form Q will be given, and you are to show that this form has the desired properties. It's discriminant minus 4d, that sounds not too bad. Primitive, that sounds all right. Reduced, yeah, we do that based on the signs of the terms. The middle thing's supposed to be less than or equal to the first thing's supposed to be less than or equal to the last coefficient. And different from the principal form, yikes. Okay. You should also check the cases considered cover all possibilities. Okay. Right, suppose d is not a prime power, good start. Then it can be factored like this. In this case, let q be of the form x squared plus cy squared. So first check, the discriminant is 0 squared minus 4ac, which is minus 4d. Good start. It's reduced because a is less than c, and it's different from the principal form. Why is this? So the principal form up here can take the value 1, and this thing cannot take the value 1 because both the coefficients are larger than 1, and there's no way for this to be the value to be the number 1 anywhere. Just this thing is this first term is either 0 or too large, and then this thing's either 0 or too large. So you can make it 0, but if you put 0 in both, but you can't make it 1. So this can't be 1. So not the primitive form, not the principal form. Oops. Are we calling these principal forms for these ones? Fair enough. Yes. We want to think about the roots. Now, key thing here. So not a prime power means that you can take out, you can factorize it like this with different bits of primes with no overlap. Okay, interesting. Yeah, so these ones we're dealing with negative discriminant, so we're not going to get any separator line. We're going to be dealing with ones which are always positive or always negative. I think they're called, I've maybe been mixing up elliptic and hyperbolic, because I think these ones are called elliptic quadratic forms, and I've got a feeling that's what I said for the last ones as well. Oops. Yeah, I'm going to say these are elliptic quadratic forms anyway. I'm going to stick with calling everything elliptic. Okay, B. The form this will work provided that b plus 1, d plus 1, because you go 4 minus 4ac, so the discriminant where A and C are coprime. Okay, this is pretty strong. You also need that A and C are coprime. You don't need them to be larger than 2 for this one for it to be reduced. A and C are coprime. I think they could be. I think maybe they could be equal. Yeah, I think they need to be. They're allowed to be equal to H in the middle, I think. For reduced is the thing I'm supposed to be checking. If D is odd, for example, a power of an odd prime, then D plus 1 is even, so it has one of these things going on. Unless D plus 1 is a power of 2. Because then it won't have any. So power of an odd prime immediately followed by a power of 2 would be a problem. That doesn't seem that likely, does it? A power of 2 immediately after a power of 3? Feels like we should solve that. But no, let's go and look at whatever C is. If D is 2 to the n, the cases we need to consider are this, since D is greater than 4. We're only talking about these cases. We only need to care about large powers of 2, because these small ones are allowed to have class number 1, right? When n is 3, take this. When n is greater than 4, take q to be that. Oh, yuck, okay. So again, we need to show they're not the principal form. That seems quite hard. Cool, okay. And when it's this one, the case of interest are n greater than or equal to 3. When n is 3, we have, so when n plus 1 is a power of 2, in that case we were worried about, which is one of the allowed exceptions. Okay, great. When n is 4, we have d is 15, and this works as in part A. What? Oh, that factorises like this. When n is 5, we have d is 31, which is a prime power. So I thought this might never happen. Yes, the way you remember it is the shapes that you get from... yes, like x squared. Like ax squared plus by squared is an ellipse if you set it equal to a constant. Gives you an ellipse. That's why it's called an elliptic quadratic form. If you put a minus sign in the middle, you get the equation for hyperbola. And in fact, what you're supposed to do is calculate the discriminant rather than twos. Then that also allows for things with an xy term in the middle. Right, I don't think I'm making any sense. I'm sort of trying to skim read loads of maths at once. When n is 4, we have this. It's 5, d is 31. Take the form that, crikey, when n is greater than 6. Use this one. Ugh, yuck, okay. I don't see an easy way to say... Well, I suppose it is what numbers can these take? And looking at small values that they can take, it's probably the way in. To say, oh, for example, this one can take the value 5, and this one can take the value of 8. But we're actually talking about d being quite large. So if you're trying to make that value using the principal form, then you don't want any of that, and then it's a question about whether you're making a square number or not. Just x squared is a different sort of quadratic form. I think it's called parabolic. Should we check? We had this at the start of chapter 5. Not there, not there. I get a tiny preview. There we go, classification. 4 types of forms. Principal, they were called principal back here. Yes, a parabolic form. If it takes the value 0 and either positive or negative values, but not both. And you have there a parabolic form, and x squared makes me think of parabolas as well. Delta is 0. B squared minus 4ac is 0, if you like. Okay. Back to page 140 something. Oh, did I get it? I did get it. Nice. Getting better on the page turns. Okay, so apparently by considering a whole bunch of weird quadratic forms, you can show that there are these other ones that don't take the same values. Fair enough. Okay. Oh, and then hard question 3. Show the class of discriminant this. It's, oh no. Oh no. The number of positive integers less than q in coprime to q. Oh, I don't like that. I don't like that at all. That seems like I'd have to understand loads of stuff. Let's go. So if I want h squared plus 4 I'm going to have to say AC. Square discriminant. When do you get this? So I'm interested in how it could be so simple. Are these all going to be mostly, maybe these are mostly not primitive. That would be fun. No, I don't think it's that though. It feels a bit like, well, my current strategy would be to split this up and say, well, H could be, if Q is even, I want H to be 0, 2, 4, 6, 8, all the way up to Q squared. Up to Q, I suppose. AC has to be the difference then. Something to do with the difference divided by 4. How many ways are there to factorise that? Complicated. Oh, I think parabolic was an option in the list as well. 0 hyperbolic is... The parabolic, I think, comes up if you have a repeated rational root to the associated quadratic by dividing through by y squared, setting it equal to 0. Because then it's single signed but can take the value 0. The 0 hyperbolic, I think, takes both signs and takes the value 0 because it's got some rational roots. So 0 hyperbolic, 2 distinct rational roots, parabolic, repeated rational root. And from quadratics, you know that if it's got distinct rational roots, then it'll have a bit in between that's the other sign, and if it's got repeated rational roots, then single signed. If the discriminant's positive, then it's if the discriminant's positive, then it's 0 hyperbolic, and you get sorry, if the discriminant is positive, then look to see whether it can take the value 0 or not. It might be hyperbolic or it might be 0 hyperbolic. Come back to my list. Let's do it over here as well. Yep. Chapter 5. Oh, why are you extracting text? You're a PDF viewer. Stop extracting text. Your job is to view PDFs. You're a PDF viewer. It used to be a very straightforward job. I don't know why you've decided to be all AI-ish about it. I don't know. Anyway. Some terminology, and we've got these different cases. Oh no, I'm wrong. Am I wrong? That's fun. Yeah, so I've been saying check if it takes the value 0, and they're saying check if it's usual discriminant's a square number. Is that the same thing? Square number gives you rational roots. If a discriminant's a square number, you get rational roots. That's nothing to do with it taking the value 0. Yes, it is. Because taking the value 0 means rational roots. If it's a non-zero, if the answer is positive and a square, then you get 2 roots that are distinct and rational. So my intuition is that you have these distinct rational roots. Some regions where this will have different values, and some regions where this thing will be 0 in 2 places. Yeah, okay. I might need to take like a screenshot of this page or something because I keep getting these the wrong way around. And there's a link to this. Right, okay. Thanks for making me think about it again. I'm so surprised by this fact. This seems weird. Can I chase it through at all? Yeah, maybe that's kind of what we're doing. What rationals can give you the discriminant of delta? Yeah, we're kind of working through cases, aren't we? To look at this. To the possibilities for which numbers that you put in, but which coefficients of the quadratic, what the possibilities are for ones that give you a particular discriminant, because there's not that many. If you want rational roots, then it's not that many rationals. I can't see how you could possibly follow this through. How could you possibly chase this? These things say... So if this is the case, then they would have to be ones where... wait, no. This discriminant's positive square, so it's the thing we're talking about, isn't it? Discriminant's a positive square, so this thing will be 0 twice. And then the thing we're asking about is the around that 0 region. So around that 0 region, what happens? Because you will have, in particular then, let's think, around that 0 region is where h is equal to q is interesting. And because h equals q gives us either a or c as 0, so we have a bit of positive number, so we have a bit of separator line. With a bit of separator line where the value on one side is 0 and the value on the other side is, let's say, negative a, then no, almost, but you can... I've got a feeling that primitive ones with the same roots are equivalent. Do I mean that? Not sure if I mean that. What's going on then? So we've got 0 minus a. 0, some number, let's put the 0 underneath. Some number a, sort of separator line, or things going on near the 0 where this value is q, and then what will you see? So you'll see q more, but this stays a plus q, so this stays as q. So you're going to explore loads of things, right? It's just going to keep going up. How does that work? How does that work? Oh, A and C could be anything. We haven't done this yet, but you get A and C could be anything. You've got infinitely many things. And the question is how many cases do they fit into? And I suppose we have these arithmetic regressions going on around a 0 region, and I think there might be 2 0 regions, but around a 0 region you get this arithmetic regression. So then what the question is something like, if a is, so these are, I don't want to think about numbers that are greater than q, because greater than q and next to 0 you'll turn up somewhere in here is somewhere in this arithmetic regression is the kind of remainder when you divide by q. So I'm interested in what that is. Some number a. We're supposed to be primitive, so primitive means that the highest common factor of a and q has to be 1 in order to give us a primitive thing, and then any choice for like this, a is between 0 and q, with where it's coprime, gives us a string like this, and they're different. So then all I need to check is that you can't have 2 0 regions for the same quadratic form. I think I know why that is, but let's try and find out. So I'm kind of interested in what happens as you branch away from this 0. These are the cases with positive square discriminant. So I'm expecting there to be 2 rational roots. So I'm expecting 2 0 regions. What do you get for the other 0 region though? So you get the same value of q. Do you get a different series along there, or do you always get the same one? Yeah, didn't we have this before? We were worried about whether we'd get, if you have 2 zeros, they could have different stuff going on around. I suppose the answer is they could turn out to be the same one. There's some symmetry that reduces this by a factor of not not even by a factor of 2, but just sometimes they turn out to be the same one. Yeah, in fact, I'm a bit worried that they might all have to be linked up, because I think this thing has to have. I think this thing has to have 2 0 regions. So then they're going to pair up, aren't they? But then it could pair up with itself. It could be another around the other 0 region. It could be the same. So I don't know how to deal with that. Yeah, I don't know how to say that we get the same thing. Hi, me, Machine Rex. Yeah, we stream at 4 now. We're now a 4 PM chill stream until maybe about 6, with a tea break at 5, which is coming up quite soon. So I'll put a note for myself here. What if 2 0 regions? So in a box, and that's a note for future James. If James comes back here, have a look at those regions, because I can't see what would stop these from folding together. And say we've got a 0 over here, and I looked around there and had an arithmetic progression where the term between 0 and q was 3. But then I explored over there and I found, oh, the other one also had another 0 region somewhere far away, with 3 as one of the numbers near there, or maybe, oh no, 2 was one of the numbers around there. I'm pretty sure we saw something like this. But then I suppose I've also got the symmetry, right? Because then I can flip it. So I kind of want them to all pair up. I want them to all pair up so that then I can say, aha, but symmetry, flipping the direction, flipping from h is q to h is minus q. Gives me twice as many. I want sort of half as many and then twice as many. Different cases then. If they've both got 0, if they've both got 0, we're going in opposite directions or something. If they've got different numbers, they pair up, and there's a reflection from swapping. If they're kind of mod q, what are the numbers around your 0 regions? If there are 2 0 regions, which I think does happen, 2 distinct values of x, y pairs that you put in the coprime, then we get that. 2 seconds. If they have different numbers, then we can do a big reflection. No, big reflection? What are you talking about? We can run it in the opposite direction, and we'll just get, instead of 2 going around clockwise, we'll have the numbers going around, like instead of going 2 t plus q, t plus 2q, we're going 2 t minus q, t minus 2q, which will be different. And the other one will flip direction as well. And if it pairs up with itself, then we might have a rotation if they're going in the same direction. We might have a reflection that switches them, that moves the sides around. It feels like only one. Yeah, I'm sort of coming around to the idea that maybe this all works out, and that whatever the matching, maybe it ends up being this. Back to bot. The username was amazing though. The username was innermost aggregation u, which, if you ever wake up in the middle of the night thinking about your innermost aggregation, like, am I really aggregating my most innermost self? Oh, crikey, who knows? I was in the middle of some flow as well. I was thinking about matching up quadratic form regions. Twitch. Right, 8 lives left. Right, okay. Right, here, symmetries of forms. This is what I'm trying to think about, switching regions. I've got maybe like a 0 region over here, and I'm thinking about what's going on near that. I've got another 0 region over here, and I'm sort of thinking, is there a symmetry that switches them round? Maybe I want to think about what's happening if the numbers are increasing in this direction and increasing in this direction, then I want to do a sort of reflection to switch them. And if the numbers were increasing that way and increasing that way, then I want to do more of a rotation to get to interchange them. But either way, it feels like there's a symmetry that I can exploit that says that actually no. Oh bother! But we consider reflections to be genuinely What do we think about reflections? We think of itself. If it's the same under reflection, we say 1. If it's different under reflection. No, this is fine. Properly different. Oh, didn't play the sound. Whoops. Properly different. So you do it like proper equivalence, which means you're not allowed to say they're equivalent by reflection. And we'd have a reflection in this direction and flips the directions of both arrows. So if they're both this way or both that way. I don't know. But then you rotate and they both change. Yeah, either way, I think the rotation is powerful. Yeah, so I think I can match them all up with rotations and end up with 1 or maybe 2. How many do I want? Just 1, I think. Maybe 2. Not sure. So I think I can get to this as like a maybe divide by 2, multiply by 2 kind of sequence. Right, tea time. Thank you, Mary, for redeeming tea time. What happens during tea time is that we all have a think about what's going on, but we also go and make a cup of tea. You're welcome to go make a cup of tea too. If you hang out here for a couple of minutes, you will see a screen that says back soon while I'm making tea, and you might see an advert. The adverts long term support charity, because if this Twitch stream ever cashes out, the cash is going to charity. I will see you back in a couple of minutes to have another think about whatever this diagram is, possibly informed by a bit of section 5.4. See you in 2 minutes with a mug of tea. Be right back. I'm back, I think. Yes, no, I think I am. Oh, that camera's weird. Try and write down this quadratic form from the previous part, the ones I'm considering, because I think I may have missed something. Because I think these ones I'm thinking about here. Everyone doing alright? Get some good adverts? Just 1 ad for Mary. Oh. Mean Machine Rex did alright as well. Got terrible ads though. Oh, dearie me. Right, good, okay. So these quadratic forms we were thinking about just now, they've got a 0 region, which freaked me out a bit. And discriminant q squared, so I just want to think about these. This kind of canonical form, what I think might be the canonical forms. So maybe of the form, and then I'm taking h equals q, and I'm thinking about different values for this thing over here. So maybe these are going to be in the wrong order, but these are not canonical, I suppose. But maybe this with no y squared term, because then b squared minus 4ac is q squared, and primitive because a and q have to have no common factors. And then I realised that one of the roots of this quadratic is the number 0, which is a bit banned in our world, isn't it? So I thought maybe it's only got 1 0, and I was worried about 2 zeros for nothing. I might have gone round in a circle here. So I think I've got 2 roots, but one of them 0, which doesn't really count, because we don't have a point in our diagram for 0. Is y the same for the roots? So I think if you turn this into a quadratic, which is something we do quite a lot, to try and find the 2 points on the top of the graph where it's 0, then I think you find a x over y. The trick we always do is divide by y squared, x over y, plus no y squared terms is equal to 0, which has a root xy equals 0, which we aren't considering. That's just not one of the points. Or is it 0 over 1? Oh, I suppose 0 over 1. Yeah, rubbish. Okay, 0 over 1. We do consider that. Okay, I've underthought it. And then x over y is, and then the other root is going to be negative q over a, which is somewhere else. So I'm a bit worried about the values going on around 0. And I'm a bit worried about the values going on around minus q over a. I suppose I could investigate those points, couldn't I? I could look at the neighbouring values. You looked at ZX, yes. You're not keen. Thump Bible, right? Okay. It's quantum mechanics, baby. It's some rules for manipulating logic gates. I don't really understand any of what I looked at. I had a quick look. It was maybe a bit mischievous of me to suggest that. This is from the work stream, by the way, if people are interested. From the work stream, where my audience is mostly people getting ready to apply for university, and part of my job is to convince them that maths at university contains stuff they don't already know about, because some teenagers need to hear this. So some teenagers think that they know everything there is to know. That maths has covered so many topics during A-level or equivalent, but actually there's loads of stuff. And perhaps it was a bit cheeky of me to have ZX calculus as one of the examples of a thing that you don't learn in A-level, because my goodness, it's really hard. Yep, the lambda calculus could also be on the list of things that you probably shouldn't tell sixth formers about. Sixth formers in England and Wales. Yeah. So one of the students I had on the show wanted to talk about ZX calculus, and we didn't get there. And then I did keep mentioning it as an example of a thing. And I've linked people in the further reading notes to ZX calculus. Oh dear. University was a bit humbling for me as well, in the sense that, yeah, there's so much stuff I don't know. It's great. I'm still learning things. Right, here we are though. Yeah, I think I will quickly investigate some of these forms. I'm going to use the Desmos tool for it though. So thanks as always to Maths222 in chat, who made a thing that helps me visualize quadratic forms using the front cover of this book model. Where, oh, this is almost what I wanted to do, isn't it? I'm going to flip around the terms so that it's how I kind of wanted it. So I think I want 7x squared minus, and then I'll go for 5y squared. That's going to be 2 in here. Oh yes, I remember this. We talked about this before. It was set up as if we were doing it before. And this one, actually, I want to be xy. Okay, so we get this quadratic form. It's got a 0 at the thing 0, 1. And then it's got another 0, which in this case is tangent to the first one. It's in a neighbouring region, but I don't think it has to be. I need to put a large number here, don't I? Like 5, so we make it about this. Good, so there is another 0 region somewhere. When x is 5 and y is 2 on a plus sign. That should flip everything around. So then there should be something over here. Minus 2/5, minus 5 over 2. So I should be looking over here. No, that doesn't look right at all. Minus 5 over 2. Over here, there's the other 0 region. So the thing I'm interested in is around this 0 region. Around this 0 region, I'm going to mark this. It's not a separated line, I'm going to mark it anyway. There are numbers that are 2 mod 5, and around this one, there are ones that are 3 mod 5. And that's kind of interesting to me. And it goes 3 minus 2. Not increasing as you go around. So a reflection of this one would give me another quadratic form with the things going in the other directions. But apparently these are kind of paired together, that the one with 3 next to the 0 and the one with 2 next to the 0 appear in the same map of all the values of this quadratic form, which means that they're equivalent. So I've got at the moment twice phi of q of these in my head, because twice phi of q, because I'm imagining around the 0 you could have the things that are a mod q either increasing or decreasing as you go around clockwise, but they're all paired up, and I think nothing's paired with itself. Let's investigate. So I'm looking for a reason to divide by 2. In this case, it's because 2 increasing and 3 decreasing are paired together. Do I need to remember that? Let's just hope for the best. Let's pick another number that's coprime to 5, like 1. So in this case, we have a 0 region over here, and we have another 0 region at minus 5 over 1, which is over here. So in this case, the regions are 1 decreasing and 1 increasing as you go around. So they've paired together, and I'm lucky that it's not 1 increasing pairs with 1 increasing, which is the case I'm trying to scribble in blue and black underneath there, right? Okay, so in each case, you get 2 zeros. One at the value 0 when 0 over 1, and 1 at the other root. And I've got 2 times phi of q things that might be going on near the 0, things that are a mod q in increasing order clockwise or in decreasing order clockwise. And I'm interested in the fact that these pair up, which gives me, so for any quadratic form, I'll explore, and you might think that you have I guess it pairs with something. Do I need to worry about self-pairing? Maybe I don't. Maybe this is just a counting argument. Maybe I don't need to worry about self-pairing. Where a quadratic form, because of the 2 zeros, always does 2 things that are on my list. Two things that are on my list. 1 increasing, maybe, so this has got 1 increasing and also 1 decreasing, which is 2 things on my list. And that'll be different from, it's not interesting to me that I can flip and get, it's interesting that if I do a reflection I get the same thing, because if I reflect and then it changes all the clockwise to anti-clockwise and vice versa. But reflections don't count. So I'm getting there. I think I'm getting there. Okay, here's what I've got. I've got 2 times phi of q as the number of things that could be going on around a 0. And each quadratic form actually takes up 2 of those, or maybe 1 repeated. But if it takes up 1 repeated, then the reflection takes up the reflection repeated. And those are different. So either something pairs with itself and the reflection is different. That's irritating, right? I don't want it to pair with itself because I was trying to divide by 2. If it pairs with itself, yeah, if it pairs with itself, if around both zeros you see the same thing happening in the same direction, then that's really annoying to me. Because I was hoping that I could be able to divide by 2. If they all do that, then I've got twice phi-q. If none of them do that, then I've got 5q. So maybe I want none of them to do that. Because I'm not allowed to just reflect and say, aha, it's the same one. So again, the same way? I can rotate? No, it's the same. It doesn't mean anything. Yeah, irritating. Okay, so I think I need to know that you don't get the same thing. Like maybe you get the same one, but you don't get the same. You don't get the same. You don't get 2 places where. Sorry. You don't get 2 places with in the same diagram with 0, a, and a plus q. You don't get 2 of those in the same diagram. That feels pretty true, right? Because we've been talking about how you've seen bits a bit like this. Oh, then it would happen again. So the reason you don't get 2 bits like this in the topograph of a quadratic form is that if it were possible to do a transform on this quadratic form such that mapped one of the points that went from 0, a plus q to the other one, then you could do that transform again. And the transform will give you a different quadratic form. And it would take that point somewhere else. So guess what happens when you take over there? So taking this 0, a plus q to the other one, would then, if you transform again, well, the transform would preserve the values at wherever it goes to. So if the transform preserves the values going from a to b, then it also preserves the values going from b to, or where's it going? I guess could the transform just swap those 2 points? Could the transform just have order 2? Not quite. Just the trash talk every time. What is James talking about? Quadratic forms, values, the big scary diagrams, right? What are they doing? Can we recognise these? If you see one, can you look at the patterns, look at the numbers and say, oh, this is 1x squared plus 5xy up to a transform? Currently the answer is no, I can't. Maybe the answer never will be anything other than that. Right, let's read about symmetries, because I've got annoyed about this now. Now I'm worried about. I had this lovely argument that says you couldn't have this twice, but then I realised that you could have A goes to B and also B goes back to A again, which is actually just describing a rotation, or yeah, just an order 2 rotation. Why can't it do that? Maybe it does. Don't know. Sort of want to look a bit further. Okay, right. Let's think about symmetries. Maybe section 5.4 will tell us. So 3 question marks over here. Okay, forgot about that. Good. 2 0 regions, and it does have 2 0 regions. It does do that. So then the question mark, I'm just going to go 2, 5q divided by 2, question mark. That'll remind me when I see this next. Here we are. Okay. Symmetries. Precise meanings this time. Let's say the symmetry of a form Q or its topograph is a transformation in linear fractional maps in Z, which sends Z goes to AZ plus B over CZ plus D with, I think we are taking AD minus BC equals 1, probably. That leaves the values of Q unchanged. Was that kept with a positive or negative? Is that from ZX calculus? Are you now learning ZX calculus at the same time? Because I said it was really hard. Yeah, go. Full value of Q unchanged. That's my page of working out. So this, the values after the transform are the same. So I'm interested in this because it's the sort of rotation I was just talking about. For example, every hyperbolic form has a periodic separator line, which means there is a symmetry that translates the separator line along a set. Hooray! If T is the symmetry translating by one period in either direction, then all the positive and negative powers of T are also translation symmetries. You keep doing it as much as you like. Identity transformation is always a symmetry, but can't be bothered. Okay. Some of them also have a mirror symmetry. Yes, we've been thinking about this because we saw because they made us do an exercise, some of them had mirror symmetry. This reflector line could contain one of the edges, or it could be in between like this. Both kinds occur along the separated line of this one. Elliptic forms can have mirror symmetries as well. Elliptic forms can have mirror symmetries as well. When this one, two topographs have mirror symmetry across the line perpendicular to an edge, and two have symmetry across the line containing an edge. Right, proposition 5.6. Let's hope this is good. A number A appears on the reflector line of a mirror symmetry of the topograph of a form Q exactly, oh my goodness, exactly when Q is equivalent to a form x squared plus cy squared, or that in both cases A divides the discriminant of Q. Yes, it does in that case. In this case, this bit's easy. You just work out the discriminant. In particular, the principal forms like this have mirror symmetry, so there's at least one form with mirror symmetry in each discriminant. Yeah, and if class number's 1, then that's it. Okay. Appears on the reflector line of a mirror symmetry of the topograph of a form Q. Exactly. There are two cases where the mirror line is like this or like this. Exactly when? The figures on the right show the two types of mirror symmetries, where the reflector line is either the perpendicular bisector of an edge or the topograph contains an edge. Or when it contains an edge at the topograph. The A and C are the labels on the left and right regions as in the figure. A and C, okay. So you get this symmetry like this, or you have this thing going on. Why is it 2A plus C? Oh my goodness. So mirror symmetry, so then you can infer this value of 0, and in this case you infer the value, because you know these three things. You can infer that the value is A, because you know the three things around the point. So you know this must be 2A plus C. HP is 0, so the form is equivalent to this. Oh, once you've worked out H. So this challenge is just idea, find H. Once you know H, then you're good. It's equivalent to a form like this. In the second figure, the mirror symmetry forces low rigid of C. This was HBA, and so it's equivalent to this. Once you know value edge, we can talk about a kind of canonical form for what that is. Conversely, these have top graphs as shown as pictures. They have mirror symmetry. Okay, that's good. Number A appears on the reflector line of a mirror symmetry. Okay. Okay. Yeah, no, I was checking that these two forms have both have discriminative by this. As the proof showed, reflector lines crossing edge in the topograph. Crossing the edge in the topograph correspond to forms x squared plus cy squared. And reflector lines containing an edge correspond to forms like this. Right, okay, so what's going on? So this has got A and A the same, and then, for example, this has got A and B different. Exchanging X and Y. Oh, right, with A's like that. What? Okay, so this one's got mirror symmetry, interchanging X and Y, and therefore must be equivalent to reflect across the vertical axis of the circular Fourier diagram, which contains an edge at the topograph. So it must be equivalent to a form like this, and passes through regions of the topograph labelled 2A plus B and 2A minus B. So you can choose, and then C is A. So this is the value. So you can sort of get it into this form if you want to. I quite like that form with the B in the middle, but you can get it into this form. At which point, I think that's good. We're going to find out. So you can mess around with the shape of the form, apparently, if you spot a symmetry. Okay, Not that bothered yet. What's proposition 5.7? Is it going to be the sort of converse? Let A be a divisor. Ooh, these A's are slightly different fonts. Look, this is maths A, this is text A. A divisor of the discriminant that is either odd or twice an odd number. Fun start. Then there exists a form like this of discriminant delta having A in its topograph. And then mirror symmetry, right? Oh no, okay. And then further, if A is square free, a form of discriminant delta with A in its topograph is unique up to equivalence. Oh my goodness. A appears in the topograph only on the reflected line of a mirror symmetry. Wow. Okay, it's got a bit number theory, hasn't it? Things have started being square free and odd or twice an odd number. Crikey. Okay, here we are. Right, the conditions can be eliminated by looking at this case. There are 3 equivalence classes of forms. Here are some of them. X squared plus 9 squared, 2x squared plus 2xy plus 5y squared. So this one I see, and I'm supposed to think, ooh, these numbers are the same. Symmetry across an edge. Symmetry with a line that goes through an edge. So like this. But 2 values the same. 2 values the same next to each other. Can I internalize that or speed it up? So what are these regions then? If I put in 1, 0, I get 2. But also if I put in, yeah, no, I want to keep y the same, but then somehow change x to get the same value twice. Keeping y the same, but getting the same value of x twice on neighbouring regions. Yikes. It's not obvious to me how to do that in general. How do you find the line of symmetry if it's of that form? Is that even true? I don't even know if that's true right now. That ax squared plus ax squared plus axy plus by squared, does this have symmetry? I don't know. I think we've shown that if you have symmetry, then you're of that form. I don't think we've shown that everything of that form has symmetry. Is it obvious that I can do something with x's and y's, swapping them around? I don't think it's obvious. Okay. Last one's got 2 sorts of symmetry. It feels like overkill. And this is something to do with the factors, right? Here we go. The positive divisors of those 6 are these numbers. The divisors that appear in the topographs are the ones that are odd or twice an odd number. The divisors that appear in the topographs, the ones that are odd or twice an odd number. Of the divisors that do appear, this all feels like magic at the moment. Of the divisors that do appear, the ones that are not square free are 9 and 18. And these appear in more than one topograph. Not square free. It's got a square in it. 18's got a square in it. And these appear in more than one topograph and off the reflected lines as well as on them. As well as on them. 9, 9, 18, 18. Off the topograph, off the reflector line means that it appears twice. At least. It's a stupid observation. Okay, what the hell's going on here? Suppose first that this thing is even. For the given divisor A, let us first look for a form ax squared plus cy squared, since this has even discriminant. Yes. Okay. We want an integer c such that delta is minus 4ac. And delta is even is divisible by 4 because you have to remember that delta is either 0 or 1 mod 4. So if it's even, then it's multiple of 4. So if a is odd and divides delta, then 4 divides delta, because delta's just got this multiple of 4 in it for free that a isn't interfering with. So the divided integer c is the other part. And once you've dividing delta by c is the same sort of thing as dividing it by 4a. Okay. It's either like this or this. If delta is 8k, then this can again be solved for c, where a is twice an odd number. What on earth is going on? No, when people say ZX calculus, or the algebra. They don't mean calculus or algebra in the kind of sense of differentiation or solving equations. We're talking about a kind of category theory thing, I think, which uses words like calculus and algebra in quite a different way. I feel bad that I've opened the Pandora's box of looking at like abstract calculus as a way of doing anything with quantum mechanics. It's not something I know anything about, so I'm trying to ignore chat. Chat's way ahead of me. Chat thinks that the category theory is fun. Okay, I'm not going to stop them. Let's look for a form like that. What are we doing? What are we trying to do? So if you can find an odd factor of delta, then you can find a form that takes the value. No, I'm going to read it one more time. Oh, you just hold it all in my head, right? Here we go. Of discriminant delta having A in its topograph, and that's a fact because these ones definitely have A in their topograph because you can put in y equals 0. So that bit is fine, as long as we can find things like this that have discriminant delta. So discriminant delta means, in this case, it's one discriminant. The discriminant is minus 4ac. So if A is an odd factor, then we're okay. If A is twice an odd number, we're still okay. So twice an odd number, divisor of A, are we still okay? Let's have a look down here. If A is odd and divides this, then 4A divides it, so we're fine. C will be an integer. Okay. Since things even, it's either this, and it's 4 mod, it's 0 mod 4. It can either be this or this. If delta is 8k, then again, when A is twice an odd number, that's all right, because we know that delta has this kind of factor of 8 in it. So that's okay. But I'm worried about the case where delta is 8k plus 4. And I think I'm going to need to use the other form for that, the other shape. Yeah, so when delta is 8k plus 4 and A is twice an odd number, this is the case we haven't done yet, because in the previous one we've got delta. I've only been thinking about delta even so far, right? Is that part of proposition 5.7? No. So we're going to have to do delta odd next. There's delta odd. It's down here. A is twice an odd number. The equation like this will not have an integer solution C, since this thing is divisible by 8. It's twice an odd number. Yeah, okay. This is divisible by 8, but delta might not be. So we instead look for a form like this. This has discriminant A squared minus 4AC, so A minus 4C. And we're going to find an integer C such that you can divide by delta and be okay. Ooh. This is equivalent to saying that delta over A is A mod 4. We have A looks like this. A is 4m plus 2, do we? A is twice an odd number, yes. We have A is twice an odd number. This feels very tedious. Sorry, number theory fans, among which I sort of include myself sometimes, but goodness me, look at these cases. Here we go. A is twice an odd number, so A is 2 more 4, good. Delta divided by A, which was 4k plus 8k plus 4. If we first divide by 2, we get 4k plus 2, and then dividing by 2m plus 1, an odd number, can only change the congruent class mod 4 by a sign. So its odd numbers look like this mod 4. So it's 1 or 3, then that might flip the sign. So this thing is still 2 mod 4, and the congruence like this is satisfied. Oh, crikey. This thing is congruent to A mod 4. Why is that good enough? So did I understand this bit up here? Equivalent to saying that there's this. So I get that if these are equal, then you must have the fact that delta over A must be A mod 4 because that's a multiple of 4. But going the other way, well, okay, this says there exists some C such that the difference over here is a multiple of 4. That's exactly what mod 4 does. But if there is such a difference causing this equivalence to be true, what does the equivalence actually mean? Well, it means that there is some number such that 4 times that number is the difference between these things, which we would then write as C. So that happens precisely when A is 2 mod 4, or at least when A is 2 mod 4, which is what you get when you do twice an odd number. Twice an odd number is code for 2 mod 4. And 2 mod 4, well, you can divide something like this by something that's 2 mod 4. Because things that are 2 mod 4 are either 2 or 6 mod 8. Oh my goodness. Okay, cool, right, load of stuff going on here. I feel the compulsion to review my entire maths knowledge. Wah! Right. We are all learning, all the time. What on earth am I learning, though? What are we doing with this? I think there's some sort of like 2 mod 4 stuff going on here. This bit is the bit that's surprising to me. Let's put the question mark over here. Let's see if we can get through it and then work out what on earth it's for. And if we know what it's for, then maybe we'll be more interested in why it's true. Okay, so what if we're talking about an odd discriminant that's taking the value, oh no, that has a divisor a, some other odd number. We are looking for a form like this, not one of the form ax squared plus cy squared, because they always have discriminant multiple of 4. As above, the condition for having such a form is the congruence delta over a is congruent to a mod 4. That's how you can find the number c, is whether or not it does this. And then this is satisfied, since delta is 1 mod 4, that's how the discriminants work. B squared minus 4ac is like asking what the congruences are for square numbers. And a is plus or minus 1 mod 4. Okay, so we're all right. Yeah, we've got a bit hard mode, haven't we? It's getting less chill the more pages we read of this book. But I think it's got stuff about square numbers in there that I'd like to know, like sums of 2 squares. Because we're so close. We have quadratic forms that tell us we're interested in questions like which numbers are in the double graph of x squared plus y squared, which numbers can be written as the sum of 2 squares. And we're now reading things that say things about the discriminant, fine, but they're telling us about divisors of these things, which feels like the punchline. I kind of vaguely remember the punchline for which numbers can be written as the sum of 2 squares. It's something to do with, well, the 2's are kind of separate, the primes, there's some sort of square stuff, and things being 1 or 3 mod 4, all those ingredients are in there. We're getting towards things like that. Are we talking about values of the quadratic form? So exists a form. Do I care about if there exists a form of this thing? Not really. I care about the converse, right? Which is to say, I have a particular form in mind. I would like to understand its values. They're sort of wrapped in a converse. Wrapped in a converse? What does that mean? We have a kind of. We're talking about the opposite fact, I think, which is, can you, given a value, given a number, can you find, better than that, given a discriminant and a number, can you find a quadratic form that takes that value? The answer seems to be, well, yes, if the divisor is odd or twice an odd number, you can find some quadratic form that takes that value and has discriminant whatever you wanted. Are those the conditions? And then also if a is square free, then it's sort of unique how you do that. Fair enough. I don't know. When I started doing this sort of thing, I thought it would be a kind of rubber duck thing, maybe, where the process of just me talking to the camera. Hello, camera, by the way. Applause for the camera. That's right, it makes my hands really large if I do that. I thought that just talking to the camera would be really useful for learning, but I think it's more than that. But the thing that's actually going on is quite different. Actually talking to chat is more than. Congratulations, chat. Better than a rubber duck. Hello from inside the camera. Oh right, crikey, okay. That's a weird thing to say. That's got me good. Right, okay, here we are. Right, okay. Okay. So they've just about convinced me that you can get away with dividing, like the leftover bit. You can get away with dividing. That there will be some number like c that you can find to put in the other bit of your quadratic form, whether it's x squared plus cy squared or the other one, axy plus cy squared. You can find some number c such that this stuff works out. You can construct c almost. Yeah, no, you can. These things are congruent, so c is the kind of difference divided by 4. And the fact that the difference is a multiple of 4 is a plus. A plus, good news. So you can construct these quadratic forms that take that value, provided that a was either an odd divisor or twice an odd, and a divisor. Kind of nonsense pause. Right, yeah, what on earth are we doing? We are now turning to the second statement, which is about square-free numbers, lucky us, and about uniqueness of the quadratic forms just discussed. So take all of that knowledge that we just got about the quadratic forms, which are sort of on shaky ground, and then try and understand that that's unique. I think. Let's read it again. Forwards and backwards with maths, right? You can, very rare that you get to go through things in the order that they're written. Forwards and backwards. If A is square free, a form of discriminant up to the A in its topograph is unique up to equivalence. So if A is square free, so square free factors, like square free factors of 36 include numbers like 2, 3, 6. A appears in the topograph only on a reflect line of mirror symmetry. So if I'm looking for factors of 36 in these pictures, factors of delta. Factors of delta correspond to h equals 0. Up to, there's a factor of 4 in there, but I think we're looking at odd or twice an odd for some reason. So where be when h is 0, which is then a reflector line? Interesting, okay. But not if it's, not if if A is square free, then not if A has any square factors in, because then it can turn up somewhere else. Let's find out more. For example, this number 18 turns up here, and it turns up here. So it's not doing this thing where we say it only appears on a reflector line, it's also hanging out over here. Yes, no, I don't get. That's as far as maths. That is as far as I got. I don't understand what it's doing with multiple inputs. I think it's maybe doing the same thing to each of them, but I'm not really sure. So I'm a bit scared because we've got this like linear operator, and I'm told that it doesn't matter whether you consider them to be inputs or outputs, but I think all those are different linear operators because they are operating on different spaces. So I don't understand how you can do the spider transform where you move one of the outputs to look more like an input. That topological deformation to me changes completely which thing we're talking about. So there's something about the number of inputs that I haven't understood. Everything I just said sort of has to be incorrect because ZX calculus is a thing and you are allowed to do that transform. So kind of by definition, I have to be wrong about all of that. And it's why I've been trying not to say too much about ZX calculus because I know that I'm wrong about like the boundary of my knowledge. Have we talked about this concept before? Where you discover something where you thought you knew about something, and then you come across new information which seems to contradict the things that you knew. This works not just in maths, but other fields as well, I reckon. So maybe there's something that you thought you knew, and then you kind of find the edges, or you find this kind of interesting contradiction where I thought the world worked one way, and then I get some more information to show that, oh no, there's actually something different going on. So somewhere in between, I thought perhaps some sort of line of logic which would go, the thing I understand leads to another thing, but there must be a mistake in there because I observed the opposite. And that's really interesting. It means that there's a step in the middle. And for me, for ZX calculus, I am near the stars. There is almost nothing that I understand. So my boundary of things that I understand is embarrassingly small. I trip over it as soon as I go. So they say we can transform these spiders, but I expect them to be linear maps with a particular number of inputs. So I've got something wrong already because I can't transform these. Combining them in some way. I don't even really know what you mean by taking 6 to give 2,3. Right, I tried very briefly to understand ZX calculus. Maybe one day Sunday streams will be very, very advanced. I would say we'll get there, but I'm not convinced we will, he says, looking back at the square free numbers. Oh, right. Oh, no. Yeah, but I don't. Yeah, this the second one doesn't make that much. I don't quite know what that operation is. When you take 6 and 2 and you get 3, that's division, and that one's asymmetric, right? So 6 and 2 division gives you 3, 2 and 6 division would give you 1/3. Whereas if you just take 6, then factorising it gives you 2 and 3, which maybe that's different from the one that gives you 3 and 2. I don't think I've understood anything about the symmetries of the inputs. So I think I've got no idea what's going on over there. Ah, there's a cheerful nihilist or something. I never know how to pronounce the I's in that. Nothing matters though, so I'll be all right. Not quite my personal philosophy, but I sort of see where people are coming from. In principle, you've got some weird operation there, which if I give you all 3 inputs as inputs, so it doesn't have any outputs, then what was it? If you move it around, so all of them are inputs, then that can't be allowed, right? Because that doesn't have any outputs. I don't know. So it's not a function anymore. It's just some numbers go in. Is that a thing that I know how to deal with? Not really. Maybe it outputs secret scalars somewhere or something, but a spider with all of its legs on one side, all its inputs, I don't really know. Is that allowed? Oh, maybe that's allowed. Okay, cool. Yeah, I don't know what that is, right? I don't know how I describe that. On a logic gate, you've got 2 wires going into your logic gate, and nothing comes out. I guess that is always allowed, but what? Maybe this is just me being confused about wire, right? Like if you take a wire, you can bend it around, and then I'm like, ooh, 2 wires go in, no wires come out, confused. But that's not actually confusing. You have like a wire, straight wire, bent wire, and I'm confused about this point where 2 wires go in and no wires come out, because I only understand wire, where 1 wire goes in, 1 wire goes out, and I don't understand this node where 2 wires go in, no wires come out. Don't get it. It's supposed to be a linear function. It's an insane thing to say, right? I think this is where my problem is, right? So you explore where your problems are. For me, humbling, my problems are always very basic. I don't understand wire. How does it work? There are 2 wires going in and nothing comes out. Like, where's the information flow? Is it a tensor product? It's got to send information back out the left. I think I need to relax about what all of these things perhaps are telling me that there's some relationship between all of the input outputs, whatever. They're all related together. Like the equation of a circle says x and y. It's not really a function x in terms of y. The equation of a circle is x squared plus y squared equals 1. Maybe that's my way to think about it. And then, so they're not really like inputs and outputs. They're just like a constraint that applies to those 2 things. The voltage going in the wire is the same as the voltage coming out the wire. Something like that. I don't know. Kirchhoff's laws or something probably tells me that like the sum of all of these things, it doesn't matter if they're coming in from the left or going out to the right, the sum of all the current flows into this point. I should probably go and learn classical, like how do you set up calculus for a normal logic gate. Right, I'm getting distracted by chat and ZX calculus, which I only told people about as a kind of joke in the first place. Right, okay, we're down here somewhere. Second statement. We got about 10 minutes, I think, on the clock. Is that going to be enough? Where's our target? What's our target? Target is that square down there to finish this proof. Oh, it's all gone away. Disappeared for a second. Scrolling very carefully. Right, here we go. This screen, 10 minutes. No scrolling, no page turns. Just me, this screen, 10 minutes, trying to understand. I can't even look back at proposition 5.7, but trying to understand proposition 5.7 on the previous slide. Right, so we're assuming that A is a square free divisor of delta. Let's see if I can remember that. Suppose that A appears in the topograph of a form of discriminant delta. Our aim is to show that there's a unique. Our aim is to show that it appears only once and only appears on the reflector line. Okay, I can see some reflections down there as well. Suppose that A appears in the topograph of a form of discriminant delta. which it can do. We just proved it can do, provided that A is an odd factor or twice an odd factor, which I think we're still assuming. Okay, if B is one of the labels on an edge of the topograph bordering the region A, is B labels on an edge. Maths 2 is also at some sort of boundary in understanding. We're all just pushing the edges of what we know, right? If B is one of the labels on an edge of the topograph bordering the region labelled A, everything is always such a long phrase in this book, isn't it? Like the label on the edge is B for a region labelled A. The jury's out what else is going on. Then we have delta is B squared minus 4AC for C, the label on the other region adjacent to the B axis. We have A and C for the labels on the regions, and we must have B squared minus 4AC for the discriminant. A is square free, odd or twice an odd number. Since we assume A divides this, it must also divide B squared. And if A is square free, ooh, fun, okay, if A is square free, it will therefore divide B. That's a fun fact. A divides B squared, A square free implies A divides B. So you can do this one prime at a time. This is a catchphrase maybe. For each prime factor in A, it divides B squared, so it divides B. And then put them all back together again to say for each prime, the product of those primes then divides B. A is square free, so you only have to think about each prime once. And you never have this situation where you take prime factors and you can't reassemble A. Whereas if you have some square factor in there, some repeated prime, then it doesn't have to divide B squared. It doesn't have to divide. The prime has to divide B. If you have a repeated prime square factor, like some sort of, if A includes 3 squared, then it is true that 3 divides B squared. So it's true that 3 divides B, but down here I want all of the factors of A to divide B. So the thing you would actually say is that what's this? Each of the primes in A must divide B once. So if A is square free, you get all of it. Okay, that's a fun step, I like that. A is square free will then divide B. So B is MA for some integer M. Okay, fair enough. The labels on the edges bordering the A region form an arithmetic progression with increments 2A. That's a lot, isn't it? Where's that come from? The labels on the edges bordering the A region form an arithmetic progression with increment 2A. 2A? So these are the numbers of that. B plus, not C plus. No, we're still going. They definitely mean B plus. The labels on the edges bordering the A region form an arithmetic progression with increment 2A. Well, let's make that happen. Let's follow it through. So the next thing will be A plus B plus C, which is an increase of C to A plus B plus 2C. So A plus 2B. Yeah, that is true. It has gone up by 2B. A plus, no. What? It's this combination, which I was doing at the start of the stream as well, to get from C plus A with difference B to A plus B plus C, and then back up a little bit and think about how that change is now reading across this edge to go from C to A plus B plus, from C to 2A plus B plus C, which is an increase of 2A plus B on that edge, on the edge, which is, compared to B, now 2A plus B, and then that happens again. So this seems generically true, that something I should be thinking about when I'm drawing separator lines or something, because this is just the arithmetic progression rule. If you have A, C with a line B in the middle, then the next line will be 2A plus B. That seems like it breaks symmetry. This arrow over here will be 2A plus B, which breaks symmetry. This one will be 2C plus B up there, but we're interested in going around the A region. Okay, Okay, so 2a plus b as k ranges over all the integers. So going around the A region, you get these things. Feels like we should be using this faster in. I've said I wouldn't change page, so I'm going to stay here for the next 5 minutes. Okay, since b is ma, we can factorise this, so they're all multiples of a, and that thing, since m is all even numbers if m is even, and all odd numbers if m is odd, we can choose k such that this is either 0 or 1, and then we've got two cases, either 0 or a as one of them somewhere, either 0 or a. Those are the two cases that we've had before. A reflected line passing through that a region. So if it takes the value a, then read around until you get to either this place where it's on a reflector line, or this place where the reflector line lines up with the edge. So it must be on a reflector line. You just have to keep looking until you find the reflector line. That's pretty cool. Equivalent to this or that. So to finish proof, we only need to see that there cannot be a form, both a form like this and a form like that with the same a and the same discriminant. I'll worry about the one being two of the same shape in a second. With the same a and the same discriminant, equating the discriminants, same a and the same discriminant, we have this, and therefore a is 4 times the difference. But a would have to be divided by 4, and that's not square free. Okay. So you can't have both going on, unless maybe you can if a is square root. It could turn up in both sorts, which is what we saw for the number 18. The number 18 was showing up. Not multiple of 4, is it? Was number 18 showing up in both sorts? So it looks like a is showing up in both sorts. Not square, not multiple of 4 though. Is the value of c here 9 and 5? The difference is multiple of 4. So is it true? I've turned the page. I said I wouldn't, and I've turned the page. So a, but here the a factor is. So I think so. Previous page had an example where I think we looked at a as 18, c prime is 9, c is 5. Oh no, c is 5. C is 5. C prime is. Oh, is it 9? I can't make this work. 18. Oh, but these are different values of a. This is 1 and this is 2. So this one. What's going on there? Why does this one take the value of 18? It's not the case that 18's not odd, so who cares? Right, okay. Maths 2 is doing quite well, and ZX calculus maybe. Not a good example of this thing going on because 18 is not. 18 is not multiple of 4, but it's also not odd. It is twice an odd number, so you might think that it would appear twice an odd number, so you might think that it would appear somewhere. Always something really simple, but then really complicated stuff going on. 18 does appear on the reflector line of. It does appear on one of these, but not both. 18? It's twice an odd number, so I would like it to appear in one of these, and I suppose it has, but the form is a transformed version of this. So is this equivalent to something like 18x squared? Right, so this these c and c prime are going to change. I'm not going to end up with 18 being a multiple of 4. It doesn't appear in both. 18 doesn't appear in both sorts, maybe. Felt like it did. Okay. I think we're going to stop there. These can't have the same discriminant, but both have a in them. So I thought we had these two with the same discriminant. It looks like 18 is appearing in both of them, so I haven't quite squared the circle of how things can appear in the form. What's this an example of? So there's this equivalence class. I think I need to rewrite this one in a form that has 18x squared plus 18xy at the front. I think. Not looking forward to that. Because then I'll be able to say, aha, 18 is appearing in one of these. I'm discriminant delta having A in its top graph. Unique up to equivalence. So what is this then? So is it 18x squared? The discriminant is supposed to be minus 36. I'm not exactly sure how that's going to happen. Exists a form like this, cy squared. So what on earth is cy squared? It's supposed to be 18 squared minus 4 times 18 times c is supposed to be minus 36. Is that going to happen? Is that going to happen? Divide both sides by 18 and you get 18 minus 4c is equal to minus 2. So c is 5. 4c is 20. Yep, good. Okay, that number there, I think, not a coincidence. Maybe a coincidence. C is 5. Okay. Yeah. We've encouraged people to learn mathematics. Hooray! Or whatever. Doesn't have to be mathematics. Quick look at some fairy diagrams, because I think I want to look at 18x squared, 18xy, and 5y squared, just to wrap things up a bit here. And that's got values like, well, I was hoping for an 18, and there is an 18, and it's got this 5, 5 pattern and 2. So that's a transform of the one that we're looking for under here, which goes 18, 5, 5, 2. So it does happen that it's in a quadratic form of that shape. It also appears in one of that shape, where I'm going to rewrite this as 18x squared. So this is, it does look like it appears in one of these, I suppose. Yeah, this is an example of it appearing in something of that shape for some A, but not for this A. Because if I write down this, then the thing I'm supposed to write down for the other term is supposed to be a C that multiplies this to give minus 36. Well, I suppose it does exist, but that's not. Is that right? No, because that's just everything in that one's multiple of 2. That's not a primitive. That's not a primitive form. Well, I suppose it's true that there exists something of that form of discriminant minus 36 having A in its topograph. So now I've got two cases. I've got 18x squared plus 2y squared, and I've got 18x squared plus 18xy plus 5y squared, and those are not equivalent. And I'm interested in the fact that 18 appears in both. Well, 18 is not a multiple of 4. So these discriminants are supposed to be equal. I think they are equal. I think they're both minus 36. And I'm supposed to have 18, 18, 5. And I've got 18 and 2 have the same discriminant. And this should fail because 18 is not square free. But it's not square free, not because of this conclusion, so I'm interested. 18 is not square free and it's not a multiple of 4, so I don't know what's going on there. Let's check it out. 18, 18, 5 and 18, 2 have the same discriminant. Equating the discriminants of these forms, we would have that 18 is 4 times 5 take away minus 5 take away 9, 5 take away 2. Well, it's not, is it? That's ridiculous. What have I done wrong? I didn't divide by 4. I didn't divide by 4. There is no such thing as the one on the left. This one doesn't have discriminant minus 36. Oh, did someone shout? Sorry. As people outside. This is not that 3 equals minus 36. Always a mistake in there somewhere, right? This is the thing again about finding, I think I understand this, but it says not divisible by 4, whereas the problem over here is 18. 18 is not multiple of 4, so I've misunderstood something to find the line between the stuff I think I understand and the stuff I think I can infer from it. And if I'm inferring something wrong, I need to back up. In this case, it's because this one, it doesn't have a form of that shape. If the factor were a multiple of 4, then I should be able to find both. B squared minus 4ac. Then I should be able to find both if it's a multiple of 4 by setting up C and C prime correctly. So the C minus C prime is the difference. Shouldn't be too hard. But 18 is not a multiple of 4, so I can't build this one. Because I'm supposed to have 4 times 18 times this, so this was supposed to be 1/2. And 1/2 is not an integer. I think we did all right in the end there. Okay, so this one, although it has the value of 18 in this shaped form, there isn't a form 18x squared plus anything y squared. That's discriminant minus 36. So minus 18. So 18 is not a counterexample to the claim on the next page that you have to be multiple of 4 and thus not square free, but you have to be multiple of 4 to be a counterexample. Because although 18 does appear twice in those pictures for not being 18 is not square free, which gives us a different problem. Oof. Not obvious whether things that are not square free always appear more than once in forms both like this. It can't be just for this reason backwards, because it doesn't even follow backwards that you have to be a multiple of 4. Right. Up to you. If you yes, go for it if you like. I didn't follow up on that thing you sent me. I'm sorry. My schedule is pretty straightforward. I'm live at 4 on Sunday, and I blather on about quadratic forms about 4 o'clock until about 6. Yeah, if they're nice. Best rodent side is a cat. Cats, no, especially if you're on a ship. Ship's cat. What you want. That's what I'm told. Right, okay. What have I learned? I've learned that there are 3 things in the class number of quadratic forms. Discriminant positive 148. I've learned to avoid ones that are not primitive by avoiding triple HAC that have a common factor, or HPQ as it might be. And then I've learned a fact about symmetries. We've only got through, what is that, 2 pages or something? We've talked about how there's sometimes some symmetries. We did all of that. Sometimes some symmetries, and we've crept across 3 pages of book. We've learned a fact that I think I'm going to struggle to remember for next week. We've learned a fact about odd factors appearing in the topograph. If they're square free, then only appearing on the reflector line and not appearing in both types. So kind of unique, although I'm a bit scared about saying unique of that form, whatever. Next time, symmetries of elliptic forms. They were doing all right. Right, okay, good. I will see you next week for some more, if you like, for some more. The stream is optional. I'll see you next week. Take care. Have a nice Sunday evening. See you next week for more quadratic form stuff, I think. It's getting good. We're getting number theory adjacent facts, I think. Not quite in the form of number theory that I recognise yet, but it feels like things might be crystallising towards sum of 2 squares. Let's have a quick look before I switch it all off. Let's have a look back at the table of contents page. We haven't looked here for ages. So we're classifying quadratic forms, and once we've understood symmetries, there's a chart of all forms. That sounds exciting. And then we might be interested in, oh my goodness, proof of quadratic reciprocity. I've never understood that before. We've never done the proof. Class groups. What do I want? I want to know. What do I actually want to know about this? Oh dear. I'd quite like to know about unique factorization. A little bit, maybe not about quadratic fields. What do I want to know? Representations in a fixed discriminant, maybe? Possibly? Right, okay. See you next time for some more of all of that, possibly leading on to this, and who knows, maybe one day even all of that. Right, good, that's the stream. I don't know if anyone else is live. If anyone else is live, Mean Machine Rex will probably know. Go and have other Twitch streams are unavailable. Right, good. As Herb taught me to say, I am ending the stream. Goodbye.